Okay, in this video, I really want to focus on the connection between energy and cellular respiration. A lot of the introductory material has focused on energy and looking at enzymes and how enzymes are involved in metabolism. And here, I just kind of want to review how energy and cellular respiration are connected. So we are ready to move into our subsequent module that is going to specifically focus on cellular respiration. All right, so let's think about what we know. Okay, from our previous modules, we know that we are going to focus on glucose, which represents our fuel for cellular respiration. And we know through the process of cellular respiration, we are going to break down glucose in what we call a metabolic pathway. And a metabolic pathway is a multi-step pathway that consists of many chemical reactions to get from your initial reactants to your final products. And ultimately, glucose is broken down in this metabolic pathway to CO2 and water. Okay? And I'm writing them in this orientation to represent that glucose has a high level of chemical energy. So this is kind of a gradient for chemical energy that I'm representing here. And glucose has a high level of chemical energy. That chemical energy is stored in the covalent bonds. And when glucose is broken down, when those chemical bonds are broken and the atoms are rearranged to form different molecules, energy is going to be released. I'm just going to use these squiggly arrows to represent energy. So here we have this energy being released in kind of smaller increments over the entire metabolic pathway until we get to CO2 and water, which are, let's say, lower chemical energy molecules as compared to glucose. I didn't write an arrow here, but let's just write an arrow up here that says higher chemical energy. Okay. This energy that is released, okay, is very important because this is the energy that's going to be used to make ATP. And as we know, ATP is the energy currency for our cells. We need ATP to do cellular work, and that cellular work can be mechanical work, chemical work, or transport work. We can think about cellular respiration in this overall summary equation. We're going to think about aerobic respiration. Here we have glucose in its molecular formula, C6H12O6. In addition to 6 molecular oxygen molecules, so aerobic respiration in the presence of oxygen. In this metabolic pathway of cellular respiration, that glucose molecule is broken down into 6 CO2 and 6 water molecules. And this is just another way to look at what we had previously looked at above, okay? Knowing that glucose has that high chemical energy, and CO2 and water have a lower chemical energy. In this process by which we break down glucose in the presence of oxygen to release its energy is a catabolic reaction or a catabolic pathway. Overall, through these multiple chemical reactions in the breakdown of glucose to release its energy, energy is released. We have a net release of energy. And of course, this is important because we know that this energy that is released is going to be used to make ATP. Now we're going to dive a little bit deeper into how energy is released from glucose as it's being broken down. And in fact, when glucose is broken down, energy is going to be released through what we call redox reactions. Now, redox is a word that is short for oxidation reduction reactions. The RED of reduction represents the RED in redox, and the OX represents the end of the redox term. And in oxidation reduction reactions, we have a transfer of electrons between reactants that release energy. And we can look at the above equation, our summary equation for cellular respiration, as a redox reaction. We have two reactants, glucose and O2, and ultimately it is a transfer of electrons between these reactants which releases this energy that can be used to generate ATP. Now, oxidation and reduction are terms that are ingrained in chemistry. We are talking about electron movement or electron transfers. And in fact, if we look at these terms in a little bit detail to kind of define them, we see that oxidation is the loss of electrons, and reduction is the gain of electrons. So we can think about that in terms of reactants in a chemical reaction. The reactant that is losing electrons is being oxidized, and the reactant that is gaining those electrons is being reduced. Now, even though we're talking about the transfer of electrons between reactants in the context of a redox reaction, what we are really looking at is the movement of a hydrogen atom. Now, let's think about this for a second. We have been through chemistry, so we recognize that a hydrogen atom is made up of one proton and one electron. Okay? So the movement of a hydrogen atom represents the movement, the transfer of an electron. Okay? Now, if we go back and look at the original summary equation for cellular respiration, I'm going to try to highlight these in different colors. Okay. Glucose is being oxidized to CO2. Okay. We have the movement or the transfer of hydrogen atoms from glucose to oxygen. Glucose is oxidized. It loses those hydrogen atoms, those electrons, while oxygen is reduced. It gains those hydrogen atoms, those electrons. And we can think about it in terms of redox reactions when we think about the breakdown of glucose. In multiple steps, glucose is going to be broken down by removing electrons in the context of those hydrogen atoms from that glucose molecule and ultimately transferring those electrons and, in general, those hydrogen atoms to the oxygen atom. Okay? Now, this isn't a direct transfer of electrons from glucose to oxygen. There are intermediates in these redox reactions that are called electron carriers, and that's the concept that we're going to review next. The role of an electron carrier is to carry electrons from glucose or a glucose intermediate, an intermediate that is generated in the breakdown of that glucose molecule, to the electron transport chain. And an example of an electron carrier is a molecule called NAD+. Oh, I'm not writing here, hold on. This particular molecule has the role of taking electrons from glucose and carrying them where they need to be as part of cellular respiration. This electron transport chain is an important step in the overall process of cellular respiration, and we'll be taking some time to review that a little bit later. But let's look at the role of NADH, and let's take a example, and let's just look at a glucose intermediate. Okay, so this is a molecule that is going to be generated during the breakdown of glucose in cellular respiration. I'm not going to draw the whole molecule out because obviously multiple carbons and different atoms, and so I'm just going to draw part of it. There's more here, more here, more here, right? Everything's here, but this is, I think, okay just for this discussion, and so we're just going to simply call this a glucose intermediate. And I'm really not concerned about you knowing every single chemical reaction that happens in this metabolic pathway of cellular respiration. Instead, we're going to take a very kind of holistic approach to looking at the subject and really following the energy through cellular respiration. And we'll see that more in the next module. Okay? But for now, let's look at how NADH acts as this electron carrier. So NAD plus and the glucose intermediate are going to represent our reactants in a chemical reaction. Okay? And we are going to look specifically at a redox reaction. We know that a redox reaction transfers one or more electrons between reactants with some energy that is released. Okay? Now, NADH as an electron carrier has the capacity to carry 2 electrons and 1 proton. Okay? And in this chemical reaction, an enzyme is going to come in and remove 2 hydrogen atoms from the glucose intermediate. And this is going to cause chemical bonds to break, new bonds to form, and we are going to end up with another glucose intermediate in the breakdown of this glucose molecule. Okay? And in addition to this intermediate, another intermediate, again, not worried about the names, this is just a product of this chemical reaction, we also have 2 hydrogen atoms to account for. Because we know in a chemical reaction, matter cannot be created or destroyed, so we have to have the same atoms on the reactant side of the chemical reaction as we do on the product side. And we know that these 2 hydrogen atoms consist of 2 electrons and 2 protons. So we know that NAD plus can pick up 2 electrons, that's its carrying capacity, plus 1 proton. Okay? NAD plus already has an extra proton in the molecule, giving it a positive charge, and we're adding a second positive charge. By adding 2 negatively charged electrons, we are essentially adding a complete hydrogen atom. So NADH. Okay. 1 electron cancels out the positive charge, and the second electron plus the second proton represent the hydrogen atom. Now we've accounted for the 2 electrons and 1 proton. That's part of the 2 hydrogen atoms that were removed from the glucose intermediate of our product, but we also have a second proton, which we are going to represent as a hydrogen ion, because the hydrogen atom has 1 electron and 1 proton. When you remove an electron, what you're left with is just a proton, or what we call a hydrogen ion. This is a redox reaction. We have transferred electrons between reactants with the loss of some energy. In this case, glucose again, has been oxidized. There has been a loss of electrons, and NAD plus has been reduced. It has gained electrons. And this NADH is a very important molecule in cellular respiration. We can think of NADH as having stored energy, and that stored energy cannot do the work of the cell. We need ATP, but we can think about it as banked energy, and if we remove that bank energy from the reduced electron carrier, we can use that energy to produce ATP. So the next thing we're going to do is take a kind of a very simplified look at what happens when NADH comes into the electron transport chain of cellular respiration. As mentioned, the electron transport chain is an important part of cellular respiration, and we're going to talk about the electron transport chain in more detail in the next module, but for right now I want to give just a brief overview or summary of it, because ultimately the electron transport chain is a series of redox reactions. And since we are talking about these redox reactions and the transfer of electrons releasing energy, I thought it was a good place to kind of add this information. All right, so we know that we consume food and that food represents our fuel. We're going to use, as an example, a glucose molecule as our fuel. And we can break down the glucose molecule, and through redox reactions, we can reduce electron carriers. And those reduced electron carriers, like NADH, come into the electron transport chain. And as we look at this figure, I'm going to make this let's make this an energy gradient. So the higher up in the figure, the more energy. Okay. And I am going to include some structures in here. And these are protein complexes, and we'll talk more about them in detail when we talk specifically about cellular respiration. But for right now, I think it's okay just to call them protein complexes. Okay. And what happens when NADH comes in is that we do a redox reaction. Electrons are transferred. And so NADH is going to transfer the 2 electrons that it is carrying to the first protein complex. It is also going to drop off that proton, extra proton that it picked up, in the reduction of that electron carrier, and then NADH ultimately in this step is becoming oxidized. It has lost electrons, and it goes back to NAD plus, and it can go back to the cell and help break down another glucose molecule through a redox reaction. And what we're going to do is we're going to actually focus on these 2 electrons. Okay? Now we know this is a redox reaction, so as those 2 electrons are transferred, energy is being released. Okay. Now, this electron transport chain is a series of redox reactions, kind of going down the chain each time, releasing energy. And so we have these 2 electrons that go from one protein complex to the next in a redox reaction. This protein complex becomes reduced. This protein complex becomes oxidized. This protein complex becomes oxidized. There's a loss of electrons, and this protein complex becomes reduced. This is a redox reaction. Energy is released. These electrons will continue to move down the electron transport chain. Each time releasing energy and they themselves holding on to a little less energy. Again, energy is released as this protein complex becomes oxidized and this protein complex becomes reduced. Now, the final electron acceptor in the context of the electron transport chain is an oxygen atom. And your book designates this as half of an O2 molecule. At the last electron transfer, these two electrons are transferred to that oxygen atom. And when that combines with two hydrogen ions, these two electrons, the oxygen atom, and the two hydrogen ions produce water, this low chemical energy product of cellular respiration. Now, ultimately, this energy that is released is going to be used to make ATP. And in the next module, we'll focus more on the mechanism by which this energy is used to make ATP. At this point, I think it's okay just to say, okay, I know that this energy is going to be released in the electron transport chain through this series of redox reactions, and this energy is going to be used to make ATP. All right, well, I hope that sets us up well for our next topic on cellular respiration. I think we'll be able to move through it easier now that we have all the background information on energy.